Hello everyone, I'm going to go ahead and explain you guys about the experiment 9 lab, which is finding a specific heat of a metal sample. Okay, experiment 9, we're going to find out the specific heat of a metal sample. First, what you're going to do is you're going to take a weighboard and you put some metals into that. Okay, and before you measure it, you will go ahead and tear the balance with the weighboard, and then when you put your metals into the weighboard on the balance, it will give you the mass of the metal, and then you're going to record it. Okay, and then you're going to take a test tube and then you put the metal into the test tube. Normally we want to put metal about 1 inch to 1.5 inch height, so we have a good amount of metal sample. And then you're also going to put a lid on that, and then you want to find out the average specific heat, so you're gonna do the same thing with the same metal sample, not a different metal sample, a same metal sample. What you are using as the metal in this experiment, the data given is for a metal copper. That's a copper metal sample, and you do the same thing. You take the same copper sample, measure it in the weighboard and get the mass, and then transfer it to another test tube. Okay, and then put the lid. So now you have two samples, and you can label them A and B, so you will know which one is which. Okay, A and B samples. And also we're going to use a calorimeter, and the calorimeter is something that is the heat will not transfer in and out, so we use a styrofoam cup with a lid, and you can have the lid, and then you can also have a little hole on the lid where we can put a thermometer. Okay, so what you're going to do is then you're going to get the mass of the empty calorimeter. So the mass of the empty calorimeter, when you are measuring, normally you measure it along with the lid. That is going to be your data B that you're going to collect, the mass of the empty calorimeter. And then what you're going to do is you're going to add about 50 milliliters of water into the calorimeter cup, about 50 milliliters of water. Okay, and you're going to get the mass again along with the lid. That's going to be the mass of the calorimeter plus the water. Okay, once you put the water into that, you put a thermometer inside, and then you're going to get the temperature of the water. That should be your room temperature water, and that you're going to write in the D line, which is the initial temperature of the calorimeter water. And in the meantime, what you're going to do is you're going to take a beaker, and then you're going to boil about 600 milliliters of water in a beaker. Let's say this is the beaker. So the water is been boiling for some time, and then you put your two test tubes that has metals into the boiling water. And then you put it on the hot plate and let it boil for about 15 minutes. Okay, boil about 15 minutes. And we do know that the water boils at 100 degrees Celsius, but sometimes there could be some defects in the thermometers. So what you do is, while the water is been boiling, when you are seeing the droplets like the steam, you put the thermometer inside the water, and you're going to get the temperature of the boiling water. If the thermometer is correct, then it should come to be 100. Okay, and then the boiling water is 100 degrees Celsius, and we've been boiling the metal samples also inside the test tube for about 15 minutes. So at that time we assume the temperature of the metals inside the test tube also reach the same boiling temperature as the water. So the temperature of the boiling solid will also be 100 degrees Celsius. Okay, so we have a hot object, and that's going to be the initial temperature of the metal. Temperature initial for the metal is going to be 100 degrees Celsius, because we boil the metal to a higher temperature. That you're going to write down at E, which is initial temperature of the metal. It will be given as 100 degrees. If there are defects in the thermometers, it could be little over 100 or little below 100. But that should not affect our reading, because if you are using the same thermometer throughout all your experiments, so then any difference would compensate, right? So it would be the same thing. So what you're going to do next is you're going to take that boiling water, boiling solid, and then you take your this is your calorimeter cup, okay, and then you take the lid off, and then you put that solid that was in the test tube carefully. You take the lid off, you carefully pour it over to the water. So you have water here, about 50 milliliters of water, but we will know exactly how much we have when we do calculate the amount. And then you pour that liquid into the calorimeter, not the liquid, solid into the calorimeter, and then you put the lid back, and then through the hole that you put the thermometer inside and see what is the maximum temperature that the water reaches. Now you put solid that was at 100 degrees Celsius, and then the water was at the room temperature of the initial temperature of the water. Water initial, which you measured at the beginning. And then once you put the metal, what happened? What happened to the temperature of the water? It will go high, right? Because what's happening? The metal sample is losing heat, and the water inside the calorimeter is absorbing the heat lost by the metal. So if you calculate the heat, what is the sign for heat? Heat is given by the symbol Q. But for the metal, what is the sign for the heat for the metal? Metal is losing heat. So the Q metal is going to be negative. Metal is losing. And then the water inside the calorimeter is absorbing the heat. Right? So that amount, once it comes to the temperature at a constant temperature, that amount is going to be equal. The amount of heat lost by the metal equals the amount of heat absorbed by the water. And we write down the highest temperature that the water reaches, and that's going to be the final temperature of the water. And at that temperature, final temperature, what do you think about the temperature of the metal and the water? Aren't they the same? They are the same, right? Because if it is difference, then we would still see the heat is being transferred between the metal and the water. Once the temperature become constant, it doesn't rise anymore, you write it down. That's going to be the final temperature for both metal as well as for the water. Okay, so at that time we say your metal and the water are at thermal equilibrium. At that time, Q metal, the heat lost by the metal, equals the heat absorbed by the water. Okay, now our goal is to find out the specific heat of the metal sample. Now how can we find out specific heat? We are going to use this equation, Q equals mc delta T. M is the mass of the object, C is the specific heat, and delta T is the temperature difference. First, we're going to find out which one do we know for all three, mc delta T. Now if you look at the metal, we are trying to find out the specific heat of the metal. So C, for the metal, we don't know. We know the mass of the metal and the delta T. So can we find out the Q for the metal? No, we cannot. What we're going to do is we're going to find the Q water, because we know the mass of the water. From the calorimeter cup, we know exactly how much we added. M water. Specific heat of the water, we can find out. It's a literature value. It's been done before, so it's 4.184 for the sea water, which is also known. And delta T for the water is going to be final temperature minus the initial temperature of the water, which also we know. So for the water, we know the mass. C and delta T. So we can find out the heat absorbed by the water. If we know the heat absorbed by the water, can we find out the heat lost by the metal? Yes, it's just the opposite amount. If Q water became like 1,000, so then the Q metal would be negative 1,000, like that. Once you know that amount, right, from the water, if you find the Q metal, then we know the heat lost by the metal, and then we know the mass of the metal and delta T, so we can find out the specific heat of the metal. So that is the procedure we're going to use to find out the specific heat of the metal. Okay, now let's see how we're going to do the calculations. Now these are the data obtained from this experiment. So we are given two trials. It's the same copper metal, two trials. When you want to find out an average of anything, you have to do the experiment for the same item. So this is for both the same copper metal. A is the mass of the metal sample for both trials. It's given to us, and then the mass of the empty calorimeter for the both trials given, mass of the calorimeter plus the water given as C, and then the D is the initial temperature of the calorimeter water given, and the initial temperature of the metal is given as 100, and the equilibrium temperature, meaning the highest temperature it had reached, is given to us as 36 and 46. Now let's see how to do the calculation. G going to be mass of the calorimeter water. How do we find out G? How do we find out the mass of the calorimeter water? Which letters are we going to use? It's going to be C minus B. B is the mass of the empty calorimeter. C is the calorimeter plus the water. So it should be C minus B. Okay. And what do you think about the delta T? H, how do you find out the delta T for the water? Which letter gives us the final temperature for the water? Which is F, equilibrium temperature of the calorimeter water and the metal. So delta T water going to be F minus, what's the initial temperature of the calorimeter water? D. So that's going to be F minus D. Okay, and then the I going to be Q water, meaning we're going to find out MC delta T. So let's go ahead and write down what we just found out. Okay, let me go back to the PowerPoint where I can write things. Okay, so this is what I just explained to you guys. Let's use a different color, blue. Okay, so the first data that we're going to collect is G. G is going to be the mass of the calorimeter water. That's going to be C minus B. If you do your calculations, C value minus B, it would come to be 44.182 grams. Again, you do your own calculations and check to see if the numbers I'm giving you is correct. Okay, sometimes I could be wrong by when I'm doing the calculations, but always check to see if you also get these calculations correct. So don't just copy or write down what I'm giving you. Okay, so that is G, and H going to be delta T for the water. That's going to be final temperature minus the initial. We have the final temperature at the F line minus the initial temperature of the calorimeter is D. So F minus D. So that is going to be 36 minus, final temperature was 36, minus the initial temperature of the water was given to us as, let me see that over here, 22. 36 minus 22 in Celsius, and that's going to be 14. And then we have significant figure 14.0, and this would be given to you in Celsius, and we learned that the Celsius and the Kelvin, when they subtract, they are the same amount. Okay, so it's also similar to 14 Kelvin, 14.0. Okay, that's your H. And then your I going to be Q water. So how did we say we're going to find out the Q water? Using the equation mc delta T. And what is M? Where do we find the M? M water. This is for the water. Where is M water? Which letter gives us the M water? Mass of the water going to be G. So you use what you had written in your G. And then the C is a specific heat of water, which is given in your handout, 4.184 joules grams per Kelvin, times the delta T. Where do we have the delta T for water? That is your H. So you multiply G times specific heat of water times H. So G we found 44.182 grams, and then specific heat of water 4.184 or joules grams per Kelvin times the H going to be 14.0 Kelvin. Okay, so Kelvin get cancelled, grams to grams get cancelled, and you will have the I, which is the water heat absorbed by water, and that would come a number similar to this, 2588 joule. Okay, that's going to be your I value. And then the next is, in your data sheet you need to find out delta T for the metal. Okay, so let's look at your data. Okay, over here. So we found Q water, and then the J is the delta T for the metal. How do we find the delta T for the metal? That again going to be final temperature minus the initial temperature for the metal. Where do we have the final temperature for the metal? Which letter? It's F, right? F minus, what's the initial temperature of the metal? 100, which is E. So F minus E will give you the delta T for the metal. Okay, and then Q metal, K is going to be Q metal. How do we find Q metal? Meaning heat lost by the metal. Didn't we say Q water and Q metal are the same, but they are opposite signs? Excuse me. So water absorb heat, metal lost. So the same amount that you have written in your I going to be written in K, because it's the heat lost by the metal, but it would be negative. Okay, and then L is a specific heat of the metal sample. We can use again Q metal equals mc delta T to find the specific heat of the metal sample. So let's see how to do that calculation. Okay, now we did I here, and then the J going to be, J is delta T metal, delta T for the metal. What is the final temperature? Which letter do we have for that? That's going to be F minus E, and your F is going to be 36 minus 100, 100.00. Yes. So make sure to write down the proper significant figures that is given in your data sheet. I might lose them along the way, but you be mindful to put the significant figures. Okay. And then 36 minus 100, what's that going to be? That's going to be negative 64. Okay, how many sig figs we have? 64.0. We have only one decimal place in the F, so we can keep it in 1, and that's going to be Celsius, which is also similar to your Kelvin. Okay. Remember now the delta T for the metal is negative, but that's okay. Okay, and then the J, and then the K going to be Q metal. K equals Q metal, which is similar to Q water, but going to be opposite sign. Where do we have the Q water? Q water is at I. So basically K going to be negative I. Right? Negative I, which is, we found as our I, which is the heat absorbed by the water, 2588, but you need to write the negative number of that. Okay, that's going to be the Q metal. And then L is that you need to find out the specific heat of the metal sample. How do you find out that? Again, we're going to use this equation Q equals mc delta T. mc delta T for the metal. Okay, now C then going to be specific heat. How do you find out the specific heat of the metal? Specific heat of the metal would be Q metal, heat lost by the metal, you divide by mass of the metal times the delta T for the metal. So if you look at your letters in your data sheet, where do we find the Q metal? That's going to be your K. You take what you have written in your K and you divide it by the mass of the metal. Where do we have the mass of the metal? That's going to be your, I believe it's A. Yes, the mass of the metal sample is A. Divide by A, and then the delta T for the metal. Which letter do we have delta T for the metal? That's going to be J. So what you have written on K, A and J will give you the specific heat of the metal. So let's see how we're gonna put the numbers and find out the specific heat. So L equals negative Q. So you have written at Q metal, which is K, is going to be negative I, that is negative 2588 joules over specific, not the specific heat, mass of the metal sample, which is A. It was given to us as 103.477 grams times delta T. What's the delta T we found for the metal? That was negative 64.0 Kelvin. Okay, now you can see when you do the calculations, you can see, so we do have two negative signs. You are dividing negatives, negative divided by negative, that would be positive. So you basically can cancel that and become positive. When you do the calculation, you will see you're going to get a number like this, 0.390. And what are the units going to be? None of the units get cancelled because you need to keep your specific heat. In these units, it's going to be joules, grams per Kelvin. Okay? Now, that is the specific heat for the metal sample you just did. And you follow the same procedure to do the calculations for your metal sample B. Trial 2. I'm only going to do the trial 1, but you follow the same procedure for the trial 2. The numbers given, same way you can use G equals C minus B and all that and calculate the trial 2 specific heat sample and write it down, both samples data. Okay, and then M going to be average specific heat of the metal sample 1. So how do you find average? Normally you find the average by adding the 2 and dividing by 2, right? So M going to be trial 1, trial 2, you add the specific heat that you get at L, okay? And then you add the 2 together and then you divide it by 2 and that will give you the average specific heat of metal sample 1. Okay, I did not do the calculation for the second one, so you will do it and then you do add the 2 and divide it by 2. Basically, this is how you're going to do. So the first sample came to be 0.390 and then you put the other number here. It's not subtraction, it's just the number, okay? And then you divide it by 2. Let's say, for example, once you divide it by 2, for example, let's say you get the average specific heat as, let's say, 0.3, let's say 0.391. We got the number as 0.391 average. Example. This is an example, okay? You don't use this. And so you write it down. And then compare your average specific heat for metal sample 1. Okay, let me show you what I'm talking about. Okay, let's go over here, and it says compare your average heat for metal sample 1 to the value in table 9.1. Calculate the percent error in your results. So you have to do that, and these are the known data. So we use copper, which is the first one. For the first trial I got 0.391, and for example for the 2 trials I got 0.392, but the specific heat for the copper, the real value or the actual value is given to us as 0.385. So we're going to use that to find out the percent error. Okay, joules grams per Celsius, which is similar to joules grams per Kelvin. Okay, so let's go ahead and do that. 0.385. Okay, how do we find out the percent error? How do you calculate percent error? Percent error equals absolute error over actual amount, actual value, times 100. And this equation is given to you in your experiment 1 handout in case if you have forgotten how to do it. And how do you find the absolute error? So how you find absolute error? Okay, so I'm going to go ahead and write it down here. Percent error is absolute error over actual value. So how do you find the absolute error is you take the actual value and you subtract experimental value. You see these 2 bars that I put at the end, that tells it's an absolute value, meaning irrespective of the sign of the value you get, you always choose the positive value. That is the absolute means. Actual value minus experiment value, which is the absolute error, you divide it by actual value, and then you multiply this whole thing by 100. I didn't have space, I just write it down over here, times 100. So for our example, what is the actual value for the copper? From the table it was given to us as 0.385. And what was the experimental value I got? That was 0.391. And excuse me, so these bars represent, that is, you have to take the positive value and then you divide this by actual value, which is again 0.385. And this number multiplied by 100. So 0.385 minus 0.391. Negative, it's going to give me negative 0.006 over 0.385. Remember, these bars represent whether you get a negative or positive, you only have to take the positive value. Okay, so basically that's going to be positive 0.006 over 0.385 times 100. That will be your percent error. And you divide this by 0.385 times 100, that is 1.56. Okay, that would be, the answer would be equals positive 1.56%. Okay, that's how you calculate the percent error. Okay, but don't use this 0.391 because I just made it up. You have to do your second trial calculations and get the average value. Okay, and that's it. And we are not going to be doing a second metal sample, so you cannot compare the two. But you answer a question in the pre-lab that would be similar to that, to understand what is the difference in the specific heats. Meaning, if you have 2 metal samples, one has a higher specific heat and one has a lower specific heat, what that means is the one with the higher specific heat can withhold more heat, and it would not heat it up quickly. Okay, for example, here we have copper 0.385, aluminum 0.9, nickel 0.4, zinc 0.389, tin 0.218, lead 0.129. So the lowest specific heat here is 0.129. The highest is aluminum, 0.9. So lead will heat up really fast compared to aluminum, because aluminum has a higher specific heat. Okay, that's how you would compare if you had done two metal samples. Okay, so that's about it. I hope you understood how to do the calculations and how to do the experiment, and please watch the virtual video so you will know exactly how it's been done, and let me know if you have any questions as always. So bye for now.